Dear students, I shall discuss about the Laplace transform application on differential equations. In this discussion, let me draw your attention towards the basic definitions of Laplace transform, assuming that already you have learnt in other lectures, and properties of Laplace transform, and direct Laplace transform few problems, and inverse Laplace transform few problems, and later on together this direct Laplace transform and inverse Laplace transform, how they are going to be applied for solving the differential equations. Hope you remember you are coming from various disciplines of engineering, that means from diploma course, and in diploma course those who have studied like civil, mechanical, electrical probably and other branches, probably you came across by solving the differential equations for some results which you are going to interpret over the physical applications. Yes, what is the type of transform operator, or what are the types of transforms which you have studied so far? In the case of differential equations, first of all you have studied the differential operator, and next you have studied its symbol which is represented by capital D, and Laplace transform operator, sigma operator, likewise few other operators even including integral symbol. These are all the operators in mathematics which play the major role from one system to the other system in any physical situation of the problem. Presently what we are going to discuss in this Laplace transform is that I am going to touch upon the discussion of solutions of differential equations, that too ordinary differential equations with constant coefficients, and we discuss in this syllabus as far as bridge course, that is MAT DIP 401 is concerned. We are going to discuss only the linear differential equations with constant coefficients. That is you are studying like the syllabus with the title, that is MAT DIP 401, and the part of that in the MAT DIP 401, applications of Laplace transform to linear differential equations with constant coefficients. How you are going to come across these two things? Let me mention about mechanical engineering, that is mechanical system means in the case of spring mass system the application goes like this. Suppose you have this is a spring and some mass is attached to that, and that mass is pulled in the downward direction and then you release it. So the spring makes the vibrations which are vertical vibrations, and this vertical vibrations can also be observed horizontally when you arrange that spring in the horizontal direction. Then this physical situation will be put in the form of a differential equation, and that differential equation is to be solved for further analysis. Similarly, the flow of the current through the circuit will be represented by means of capacitance, resistance, and then inductance, like that the second order differential equation and first order differential equation, because first order differential equation in the case of flow of the current through the circuit will be represented by means of first order differential equation without capacitor, and when you attach the capacitor for circuit, then it leads to second order differential equation, formation of second order differential equation, like that. Then what we do with by forming these differential equations in the engineering syllabus? In the engineering syllabus we construct these equations according to the application situation, and then we think of method of solving these differential equations, and not necessarily this Laplace transform is one among the operators which operates on the differential equation to solve and to obtain the particular solution for the interpretation. But there are several other methods to solve the differential equations. When you started studying differential equations, probably the very first method, if you recall, the very first method is separation of variables, the next method is homogeneous differential equation, and its next method is non-homogeneous differential equation, and next method is exact differential equation, and next method of solving it as reducing to exact differential equation, and next method is Bernoulli's linear differential equation, and there onwards if all these techniques fail, then we will switch over to if it is multiplied by constant coefficients, and we can consider the differential operator and then convert this differential equation into the auxiliary form, and then that auxiliary form of the differential equation will give the roots of the differential equation, and then we will sort out those roots in the form of real and different, and the second case as real and repeated, and the third case as imaginary roots. Accordingly, we will fix up the solution for the application problem. But in this Laplace transform, what we are going to do, in spite of having all these techniques to solve the differential equations, you must remember that when most of the methods what we studied starting from separation of variables up to the last method in the list of solutions of techniques of solving the differential equation, when all those methods fail, then we will think of, when initial conditions are given, we will think of how this Laplace transform operator operating on derivatives and elimination of these derivatives by with the help of a Laplace transform operator, and how we are going to solve this one. That is the material included in this topic, that is applications of Laplace transforms to linear differential equations with constant coefficients. Yes, what is the meaning of linear differential equation? One must know the nonlinear differential equation and linear differential equation. So, linear differential equation is one, and the dependent variable, which one you call it as a dependent variable? For example, in this function y equal to f of x, that is y equal to f of x. This is explained as a basic concept in the sets, functions and relations. When we form this relation, that is y equal to f x, right side x is called independent variable and y is called dependent variable. When x is called independent variable means it takes its own value, and y is called dependent quantity because it depends on what the value of x takes on its own. Therefore, y becomes the dependent variable. Now, in this case, the differential equation, when you write derivative, that is dy by dx, that means it is easy to understand the numerator symbol, that is y, depends on x, then y is a function of x. Then differential equation do arise in various forms, and our job is to solve the differential equation and the solution for y in terms of x as a functional relation which you are going to obtain. For example, the vertical vibrations and also through the circuit, flow of the current is represented by means of differential equation. There also we take the solution of this derivative or the differential equation, and whichever the method is allowed to write the differential equation. Basically, we will look back to the elementary definition, basic definition of Laplace transform. You know that basic definition of Laplace transform goes like this. These are the operators, that is L, Laplace operator, integral operator, differential operator, inverse Laplace operator, and so many other operators are there like this. But we are much concerned with these four operators in our discussion for this bridge course syllabus. What is the definition of Laplace transform? The definition of the Laplace transform is nothing but an integral equation. What is that integral equation? When any integration you write, like this is the integration, it is given, integral equation runs between 0 to infinity. That means this is the function on both sides which you are going to replace, and with respect to t we are going to integrate, and afterwards, after the integration process is completed, then you will put it as t is equal to 0 and t is equal to infinity. You are getting that value as fs. In other lectures, I am sure that you have studied the definition of this Laplace transform and their properties in detail with the derivations, and I will make use of all those derivations, and I will make use of all those inverse Laplace transform derivations, and I will make use of all those problems whatever you solved in the direct Laplace. This is called direct Laplace transform. That means L is written and L is applied over the function. You should not read this one as L into ft. This is Laplace transform operating on the function gives function of s, because t is eliminated through the integration. Therefore, this is called direct Laplace transform, and it is nothing but this function f of t will be replaced by various values. Values, for example, this f of t will be replaced by, basically it is a constant, and next is exponential term, next is trigonometric function, next is product of trigonometric and exponential, and next is product of constant and trigonometric, next is product of constant, trigonometric, exponential. Another thing is even algebraic term also. So that Laplace transform will give a definite conclusion when this f of t is replaced under the integral sign, and it contains the variable t. With respect to t, you have to integrate, and then you have to put the limits, so that ultimately you are getting the result in the form of s, but not in the form of t. Therefore, it becomes the function of s, and this function of s will be taken like this. For example, f of t is equal to f of s, and f of t is equal to 1, that is if it is a constant, what I was telling just now, then 1 you are going to replace under the integral sign, and it becomes e to the power minus st. When you are integrating this e to the power minus st, then e to the power minus st gives the integration as e to the power minus st divided by minus s, and it applies and it takes the limits over, that is t equal to 0 and t equal to infinity. You know that e to the power minus infinity is 0, and as a result simplification gives us afterwards t is equal to 0, e to the power 0 is equal to 1, and then 1 by s. This is the case of constant, and the next one is case of algebraic term, that is f of t is equal to t to the power n. Then algebraic term is replaced under the integral sign, and by the by taking the integration by product rule for n times, you will achieve the result. That result is supposed to be n factorial divided by s to the power n plus 1. First integration gives, that is n divided by s to the power 1, and leaving the integration with reduced degree, that is t to the power n is there in the left side, and t to the power n minus 1 remains. After once you take the integration, that comes to be n divided by s to the power 1, and the integration under the integral sign you will be getting e to the power minus st, and the same t to the power n is going to be reduced here as t to the power n minus 1. All these derivations in other lectures you must have already attended, and then you must have noted down all these results and the derivation. For especially in this derivation, n times you have to integrate. That means 1 or 2 times we do this procedure, and stereotype the coefficients are going to fall like n, then n minus 1, then n minus 2, and so on up to, that is n minus of n minus 1. That is the last term, because and n is greater than 0. Last but one term is n minus of n minus 2. On simplification you are getting it as 2, on simplification you are getting it as 1 for the n times integration. From that side, means from the last term towards the first term, 1 into 2 into 3 into 4 up to n will be taken as n factorial. That is all about the basics of the some results which we have discussed as Laplace transform. Another thing is exponential term. So that exponential term, in the similar fashion, if you do that, here ft, in the basic definition of ft, Laplace of ft, then ft is going to be replaced by e to the power at. So this term is going to be multiplied to exponential term, that is e to the power minus st, and basis same powers can be added by taking minus t outside here, and then the integration comes to be e to the power minus t into s minus a divided by minus of s minus a. Then simplification comes to be again putting back, that is e to the power minus infinity becomes 0, then it gives 1 by s minus a. Next is Laplace transform of trigonometric function, that is L of sin at, that is equal to a divided by s square, it should be plus a square. Here I will do this correction, this is in between plus sign should be there, and cos at, that is L of cos at is equal to, that is also function of s we call it, and it is s divided by s square plus a square. As you all know, during these derivations you remember, and it is easy to put it in the list of all these results. For sine function, numerator is a and denominator s square should be plus a square, and for cos function, that is s divided by s square plus a square. And for sine hyperbolic function, only thing you are going to replace that sine hyperbolic at. You must have studied in complex numbers what is the hyperbolic function expansion in terms of exponential, that is sine hyperbolic at you are taking in the complex number as e to the power at minus e to the power minus at. This will be replaced under the integral sign, and then you will do the integration, then you are getting it as L of sine hyperbolic at is equal to a divided by a square minus a square. So this is what the result above, along with this correction as plus sign I have to do that, and then here in the hyperbolic function it should be minus, in the simplification you are getting, and in the ordinary trigonometric function it should be plus sign. And similarly this is L of cos hyperbolic at, you know the formula from the same complex number chapter, that is e to the power at and plus e to the power at divided by 2 from the hyperbolic functions. If you replace that function under the integral sign, then it comes out to be Laplace transform of cos hyperbolic at is equal to integration of 0 to infinity e to the power minus st into e to the power at plus e to the power minus at and divided by 2. On integration and simplification, that gives s divided by s square minus a square, and then comes, that is another property, that is a linearity property, we can write like that. Laplace transform is applied to different functions, that is f of t, g of t and h of t, followed by respective constants like a, b and c. Accordingly you will write individual application of Laplace transform. Then what we do here, Laplace transform of derivatives which we have to take, and those derivatives, how those derivatives we are going to write using this basic definition of Laplace transform. I will discuss the part which you are going to discuss using this basic definition. Yes, I would like to remind you once again, after studying all these things, you have learnt Laplace transform on the three important properties, that is a shifting property, derivative property and then integration property, that is division property. Using these properties you will write the results whenever under the Laplace transform not a single function is appeared, but the function is multiplied by exponential and the function is multiplied by algebraic and the function is divided by algebraic term as t. These three properties will play the major role in discussing some of the products on the Laplace transform when you are going to solve the differential equations. In continuation of this discussion of Laplace transform, you must have studied also the inverse Laplace transform, and in the inverse Laplace transform, this L of f t what you have written here, this is if L is shifted to the right side, that becomes L inverse of f of s. That means when we have the statements in our questions which are to be discussed contain the variable as t, and the application of Laplace transform gives the function of s, and in the next part of that completely opposite type of discussion in the first chapter whatever you did it. That means function is given in terms of t, applying Laplace transform you are getting the final result in terms of s, and inverse Laplace transform gives you will be given the statement in terms of s, and you need to solve that function of s by applying, that is Laplace inverse, and you must get it back, that is f of t. Same whatever the properties, all these list of properties and derivations which I explained so far, will be written in the reverse order, that is by applying inverse Laplace transform to the other side, and you must get it as, that is function of t. This is all about direct Laplace transform and inverse Laplace transform. Few other important results which we studied in the case of direct Laplace transform and also the inverse Laplace transform. In the case of direct Laplace transform, you have studied another important theorem, that is periodic function theorem. That periodic function theorem we do require when the given function is said to be periodic, and then the function is going to be explained by means of some other equation, and that equation is to be studied using the periodic function theorem concept. And next is unit step function will also be to be studied in the direct Laplace transform. And in the case of inverse Laplace transform, you must have studied convolution theorem. That is convolution theorem in the case of inverse Laplace transform. You will be studying that convolution theorem to release the product of two terms, that is when under the application of Laplace inverse. That Laplace inverse, I will write all those list of formulas in my due course of lectures. That means as and when I require these results to be applied to solve the problems, then I shall mention that the final result of all these basic concepts and other required list of elementary Laplace transforms and list of elementary inverse Laplace transforms. I am sure that now I have given the hints, all the hints for what purpose you are studying in the engineering course the Laplace transform technique. Finally, I will remind you once again, Laplace transform is one of the powerful technique to solve. I have mentioned in my introduction topic, that is Laplace transform is one of the most powerful methods used to solve linear differential equations with constant coefficients. The solution of non-homogeneous differential equations involving discontinuous periodic functions, and we have solved these which can be solved easily using this method. Here the initial conditions are always will be given, because without initial conditions you can't reduce the problem statement into the Laplace inverse ready form. So without that you cannot proceed to the write the solution of that particular statement. Now I will start with Laplace transform application on the differential coefficients. Today I shall discuss in the remaining lecture the derivations of all these transforms of derivatives. This is the heading, transforms of Laplace transform on derivatives, because you will come across first order differential equation, second order differential equation, third order differential equation. You must have learnt already different methods of solving the differential equation, and we are going to study Laplace transform in detail for these linear differential equations with constant coefficients. I hope these are the few topics. This is for the learning material in the classroom, and for examination point of view, this is to be treated as third chapter in your syllabus, and which will give the questions, different questions from all these topics. That means basic definitions, elementary Laplace transforms, periodic function, next is unit step function, and problems on direct Laplace transform, and then inverse Laplace transform, convolution theorem, and differential equations. Let me confine my discussion only to the differential equations using Laplace transform operator. Let me see how this Laplace transform operator is going to be applied on the differential coefficients. The first order derivative, for example, the first result L of f dash of t. As you are seeing, all these elementary functions are giving these results in the form of S when Laplace transform operator is applied on these functional values, that means f of t. Then as a result you are getting in terms of S. Here also I am going to show the same thing, L of f t. Then how this is L of f dash of t? By knowing L of f t, what is the definition of that L of f t? This is the definition. This is the definition, 0 to infinity e to the power minus st ft dt, that is your definition. L of ft is equal to 0 to infinity e to the power minus st, and f of t dt will be written as f of s. And along with this you need to know L of ft is equal to fs implies f of t is equal to L inverse f of s. Otherwise, L inverse f of s is equal to f of t. That means what you have to conclude during this discussion is, you are given in terms of t, you have to write the answer in terms of s. You are given in terms of s and you need to write the answer in terms of t. This is by direct Laplace transform and this is by inverse Laplace transform. Right. The first result goes like this, L of f dash of t, and using this basic definition you write on the right side 0 to infinity, that is e to the power minus st, and then f dash of t, it is dt. Dear students, you remember different authors give different type of notations. This is f dash of t, some books they write, in some books y dash of t, in some books they write, in some books x dash of t, in some books they write like that. So whatever it is there, the principle is Laplace transform is going to be operated on first order derivative, then you have to discuss the result in terms of s, that is all. Let it be any notation. Now this is to be integrated using integration by parts. This is to be integrated using integration by parts means how to treat or how to select which term as first term and which term as second term. You remember already you must have been much familiar with when you studied these elementary Laplace transforms, and you came across of handling the product of different functions under the integral sign. For example, if you observe this elementary Laplace transforms, that is this one, t to the power n is the algebraic term. There you must consider this term as, that is L of t to the power L of t to the power n into ft must be written as L of exponential term into algebraic term type product under the integral sign. Okay. Then why to select first term as algebraic and why to select second term as exponential? But in this case we are going to select exponential as first term, and f dash of t, it is not algebraic, f dash of t it is a derivative, that we are going to select it as, that is second term. You know that basic purpose of studying integration by parts is this much, to release one is, that is inverse trigonometric function, second one is by choosing algebraic term as first function, because on the successive differentiation that term is going to be vanished, and if the derivative term comes, to remove the derivative you have to go for the integration. What is the basic formula for integration by parts? By product rule. What is the basic procedure in the product rule? That is integration u into v dx is equal to u into integral of v dx minus integral of differentiation of first function, that is u dash, into integration of, that is v dx. Let me repeat, this statement you have studied for one time integration. One time integration means this is first if I choose, and if I choose this one as second function, first into integral of second minus integral of differential of first into integration of second. This is once integration. And similarly another time when you are going to integrate, you will continue with the same statement, but some authors they conclude this by iteration process. What will be the general formula for integration by parts? That general formula goes like this, that is u1 v, otherwise plus of minus of, that is alternative plus minus you are getting, and u dash, that is first into integral of second, that is u into v1 minus u dash into v2 and plus u double dash into v3 and minus u triple dash into v4 plus so on. This is without showing this integral sign. How this goes? Listen, u into v1, that is first without integration, but second is integration, and minus integral of differential of first means this is u dash, and the integration of second function is v2. So, ultimately minus u dash v2 like that. So, this is called generalized formula, and it has been named also as Bernoulli's formula. So, at this level, for studying this Laplace transform for derivatives, that much generalization is not required, only for the one time integration by parts is more than sufficient. Then you are going to declare this result as follows. Then this integration gives, using this formula, that is first function e to the power minus st, and the second function f dash of t for integration, first into integration, that is f of t, but the limits you have to show for this product, that is 0 up to infinity minus integral of differential of first function, that is e to the power minus st and multiplied by minus s multiplied by minus s, I am sorry, then integration of this f dash becomes f of t, it is dt. I repeat this, and in your study contents, that means materials, or if you had prepared your contents in the form of some index, include the formulas in whichever the step you are going to use in your index. List of formulas you must add. This is integration by parts, and now you are going to apply the limits, and in the list of formulas that also to be shown like e to the power minus infinity is always 0, that is e to the power minus infinity and f of infinity minus, that is t is equal to 0, that is e to the power 0 and f of 0. Application of these two limits is over, minus, this minus and one more minus becomes plus sign, inside the integral symbol 0 to infinity e to the power minus st f of t, it is dt, but in this case e to the power infinity is 0, that means 1 divided by e to the power infinity. So, 1 divided by e to the power infinity is equal to 1 divided by 2.771 whole to the power infinity. This is 1 by infinity and the answer is 0. Therefore, first term gives us 0 because e to the power minus infinity is 0, and finally we are left with the second term and third term. What is the result in the second term? Then e to the power 0 is 1 and f of 0, it is a functional value at t is equal to 0. So, we do not know the value of this one, then you need to write the same value as it is. Therefore, minus of f of 0 multiplied by e to the power 0 is 1 and plus of, this can be written 0 to infinity e to the power minus st f t dt as it is according to the definition. Here f dash we reduced it to f of t, and this integral we are going to write L of f t as it is you write. Now, without any hesitation you can write this term as L of f t. Therefore, it is customary to write this term is first L of f t minus f of 0 for L of f dash of t. This is the case of Laplace transform of derivatives. Then Laplace transform of derivatives for the first order differential coefficient, this f dash of t like this, or L of, some authors they write y dash of t is equal to, some authors they write L of y of t minus y of 0. That means f dash of t and y dash of t, they are all giving the same meaning, that is first order derivative with respect to t. So, this is the first result which plays the role in solving the differential equations when we apply it to the first order derivative. Now, second order derivative in the same type we are going to study, that is L of f double dash of t. Second result, L of f double dash of t. L of f dash of t, that is written, and solve applying this integration, we remove that derivative and we are written functional value. Now, we are going to write for second order derivative with the same type of procedure we have to solve, because these are all the ready results to solve the differential equation. Then in the similar fashion, if you put it under the integral sign, f double dash of t is equal to 0 to infinity e to the power minus st f double dash of t, it is dt. Do the same procedure here as you did for the previous result. This is differentiation is to be taken for integration, because you have to remove the derivative, is only by integration it is possible. Then first term is exponential term is to be selected as first function, and this is to be taken as second function. When you apply this integration by parts, first function as it is e to the power minus st, and f double dash becomes f single dash, that is f dash of t, and this product once again is to be taken for the application of limit 0 to infinity, minus integration of differential of first term, that is minus s e to the power minus st, and f double dash becomes f dash of t, it is a dt. F double dash becomes f dash, that is f dash t dt. Now, already I told you that when you are replacing this t by infinity and t by 0, this is e to the power minus infinity, that becomes, so e to the power minus infinity and f dash of infinity, and for the lower limit e to the power 0 into f dash of 0. There you had f of 0, there you had f of 0 from which was done from f dash, which was reduced without derivative, and here it is done from f double dash and it is reduced to f dash, but t is equal to 0. This is functional value, we call it, whether in the form of derivative form or it is not in the form of derivative, but this is called functional value, this is called functional value. These type of symbols in the engineering problems will go as the main considerations when the values are given. That means if flow system, for example in the fluid mechanics, that is for civil engineering, mechanical engineering, even chemical engineering, people are going to discuss about the problems which are related to the flow of fluid through the pipelines, the flow of fluid through the open channels, and the flow of fluid through the straight surfaces and flexible surfaces, even flow of heat through the conducting metal bars, and flow of the current. Sometime back I was explaining flow of the current through the circuit. When we come across these situations, even in the case of in the electronics and communications branch, there the digital signal processing subject, how the sharpness of the signal is going to be represented, there also we write differential equations, and there we consider this Laplace transform along with the series solution of Laplace transform, that is Bessel series and also the Fourier series, that is with Euler constants. Then fast Fourier transform also is popular in getting the sharpness of the signal in the case of digital signal processing. So, engineering problems will be continuously with the support of these basic formulations which are contributed from mathematics. One among the main chapter is this Laplace transform, where differential equations people are going to handle, even including easy type problems up to the tough variety of the problems they are going to discuss by application of these elementary techniques then Laplace transform techniques, then series solution techniques, and also the numerical techniques. The numerical techniques probably you have studied in the case of interpolation chapter, and also the numerical differentiation and integration, and so many other techniques which you have studied, like Picard's method, Euler's method, Taylor series method, and then Runge-Kutta method, and then predictive corrector methods to solve the differential equations. Where these functional values will play the major role, we call them as initial conditions. The first initial condition is f of 0, and second initial condition is f dash of 0 if it is second order differential equation. If it is third order differential equation, the next derivation I am going to write, it will be reduced to the second order derivative with the functional value at t is equal to 0. Fine. Minus becomes plus sign, and this is yes, let me keep it outside this one, yes, and 0 to infinity, and here I think I left it, here also yes, here also that is yes, that I did not make a carry forward, here also yes, and here yes becomes the coefficient for this integration, and e to the power minus first into integral of second minus integral of differential of first into integration of second. Okay, that is e to the power minus st, and f dash of t, it is dt. So, as I told you that e to the power minus infinity is 0, so therefore this term becomes 0. Next, this is equal to e to the power 0 is 1, and 1 into it is f dash of 0 plus s into. Now, it is very important that second term is to be replaced. You need not to move further in order to solve once again this one by integration by product rule, because already first result is available. Simply you can replace these two terms in place of this one, integration under the integral sign, that is first order derivative. What is that first order derivative? If you write that back in the form of, that is L of f dash of t, without any hesitation I can write this one as L of f dash of t. This is your first result. This is your first result already you have derived. For what purpose? Laplace transform of first order derivative. That is first order derivative is f dash of t. So, now I represented when f dash of t occurs under the integral sign, that I am going to write like L of f dash of t. Therefore, that is equal to f dash of 0 plus s into L of f dash of t. Now, what are the results? F dash of 0 plus s into this L of f dash of t, write both the results in place of L of f dash of t, s into L of f t and minus of it is f of 0. Your integration procedure is over when once you replace this, because it is already done from the first result. What is that? That is equal to f dash of 0 plus of s into s, leaving as s square, and L of f of t, minus this s is to be taken, that is minus s into f dash of f of 0, that means s is to be multiplied. Now, it is customary to write as you written the equation number 1, that is Laplace transform, this is called transform of derivatives, that is Laplace transform of first order derivative. Here Laplace transform of second order derivative takes the expression, because you need not to solve once again when we start the applications of these transforms of derivatives in the problems. Then this goes L of f double dash of t is equal to, it is first term should be with highest degree of s, that is f of t, and minus next its lower degree of s, that is s into f of 0, and next term is here it is minus sign, that is f dash of 0, and here also minus, then minus of it is f dash of 0. So, this I can call it as equation 2, and this is the result for will be used for second order derivative. That means first order derivative, this is the expression, second order derivative, this is the expression. When you come across first order differential equation, you must restrict up to here the utilization of this result, and when you get second order differential equation, you must restrict of using both, that is first order and second order, if both the derivatives are appeared in the differential equation. That means these things will be easily met, these things will be easily handled when initial conditions are given. What are those initial conditions? In the first result, f of 0 you expect, and in the second result, followed by f of 0, f dash of 0 is also to be expected. That means first result contains the without displacement the functional value, and second result contains not only that value but also the displacement. Displacement is nothing but change in y with respect to x. That means change in y with respect to x is represented by f dash of t, and that f dash of t is nothing but y dash of t, that y dash of t is nothing but dy by dt. That means that is the derivative which explains at t is equal to 0 will be taken as it has to act as second initial condition. Therefore, the problem with these initial conditions will be together called as initial value problems. That is the main purpose of studying this chapter. I would like to stop up to here today, and if you have any questions you can ask, so that I will answer those questions.